All right, kids. So, upon Ohio State just winning, let's see if I can't get this together so you can watch it tomorrow morning. All right. What we know so far is that valence electrons determine reactivity. The number of electrons you have on your outermost shell when two atoms encounter each other will be sort of the first defense of that atom and sort of be the way an atom reacts to its surroundings. So here's hydrogen with 1, and here's oxygen, which has 6, and that will be how they interact. That'll be the first interaction between atoms. So that's why valence electrons are important. Noble gases are the most stable. They have 8 valence electrons, and stability is the goal of atoms. We've seen this already with the electron configurations, the fact that you want arrows all going up when possible. You want arrows up and down filled up when possible. So stability, like noble gases, is the goal of atoms. So what we're doing now is periodic trends. And the basis of periodic trends is all about attraction. And I tried to make that point apparent by putting on a blonde wig and whatnot. But the point is that as you get closer to noble gases, things start really wanting their electrons. The electron desire goes up toward helium, fluorine, this area. Noble gases love their electrons, they're stable. Halogens really need just one more electron, so they love the ones they have. They'd love to get another. Oxygen, sulfur, very close, and very much meaningful with electrons. Whereas on this end of things, the cesium, francium side of things, very far away for them to achieve electron noble gas status by gaining electrons, a whole bunch of electrons already. So this side of things does not have that big a concern for electrons. And remember, hydrogen is a non-metal. It's usually, when we talk about periodic trends, going to come on the non-metal side of things, somewhere here between carbon and nitrogen. All right, we'll talk about shielding in a second, but the video I showed you with Booboo Jeffries and Scorpionox was the best fighter in this game. Booboo Jeffries was a new one. Her weakness was fighting and group settings. Her strengths were a relationship with her mom. Her Rihanna and Beyonce attacks had no damage. So she was not much of a fighter. He was very much of a fighter. So on the scale of elements, Booboo Jeffries would come down here in this area as not a huge fighter for electrons, and up here in this area is where you would find Scorpionox. So the first of the periodic trends is electronegativity. That would be the measure of an atom's ability to attract additional electrons, so electrons beyond what it already has. That is why noble gases are not involved in these. Noble gases already have all the electrons they need, so we don't really apply a grade to them. So the highest grade is 4, and the lowest grade, if we can see what cesium is, cesium is a 0.7. And it goes sort of in a trend. It increases as you get closer to fluorine. There's a little bit of a bump here, and we can talk about that in more detail. But the fact of the matter is, and again, you see hydrogen should be over here by carbon, but there's an increasing trend as you get over here toward fluorine, decreasing as you get here by cesium. So this is sort of the Booboo Jeffries side of things as far as wanting electrons, and this is the Scorpionox side of things as far as wanting electrons. So electronegativity increases as you go up toward fluorine. First, ionization energy, which is the energy required to remove an electron you already have. So rather than just fighting over an electron like this situation, now it's just the electrons you have. So the noble gases come back into play. You can see they have the highest, certainly these two, and then argon is much different than fluorine. Hydrogen, again, much higher than you would expect for a metal. That's because it's not a metal, it's a non-metal, and it would actually come in here around carbon and nitrogen. And that's because hydrogen is one away from being its noble gas helium. So it's kind of like a halogen, and also hydrogen just has the one electron. So if you can actually wrestle it away, it's not got much else going for it. So that's why it's still not as good as a noble as a halogen. Anyway, all right. The trend here, though, as you see, increases as you go toward fluorine. As electrons become more important, the heliums and whatnot, they tend to have higher energy to remove an electron. And it decreases as you go down. As something has more electrons, each electron becomes less and less important. So that's why the general trend is as you go down, it decreases, but it increases as you go across, which is adding electrons across a period from sodium over to argon. You're adding an electron each way, but argon has more than sodium for ionization energy because it has a greater stability that you're breaking up. All right, so then the last of these trends that we go over is atomic radius. Now, atomic radius also has everything to do with attraction. Up here, where electrons are important, attraction is important. They're going to keep those electrons very tight and close in. So they're going to have a very small radius. Down here, where electrons aren't important, where they won't fight you for electrons, they're going to be very large radii because they just let those electrons sort of fly around wherever they want. So think about, again, what an atom looks like. You have your nucleus, and then you have your electrons spinning around the outside. So if you don't really care to keep them close, you're going to have a very big radius. And if you do care to keep those electrons close because you're feeling they're so meaningful, you're going to have this very tight radius up here. So another way to think of that, there we go, decreasing size as you go up that way. So this trend is the opposite, if you want to think of it, of the other two, in the sense that things get bigger as you get to the other corner, whereas ionization energy gets bigger as you go to helium. Electronegativity gets bigger as you go toward fluorine. But the reality is it's for the same reason. It's all about the attraction, and the more attraction something would have for its electrons, the tighter in that would be. So another way to think of that is a shepherd with sheep. Here's a shepherd who really keeps his sheep in control, very much keeping them in a distinct area. That would be something more like here, where we have very small radius that he's taking up, whereas the shepherd who sort of lets his sheep wander, because one could say, cares a little less about one getting poached or picked up by a wolf. Therefore, he would be more like here in the cesium area. He doesn't care as much about his electrons, so he's going to cover more area of a field. All right, another way to look at it, as you go down the group from lithium to potassium, you're adding rings. Every period is another energy level, another ring around the nucleus. So if all things being equal, one electron in the outermost shell, these atoms will get bigger as they go down a group. So we're going down a group from lithium down to potassium in that case. They're going to get bigger because you're adding a shell every time, adding an energy level, and that inherently is going to just make them bigger. However, when you go across a period, so sodium across to argon, you're going to have more and more electrons in that outer shell. That outer shell becomes more and more important. It gets drawn in more and more by the nucleus. So this nucleus, which has 11 protons, there are 10 electrons. 10 electrons here, sort of occupying the attention of those 11 protons. So this one can kind of go off on its own and make the radius bigger. Whereas here, when you have 3 with aluminum, now that outer shell has 3 protons sort of looking out for it. There's still 10 electrons in the inner circles. So 10 electrons for 10 protons. There's 3 protons trying to attract these outer electrons. And then here you still have 10 electrons in the inner circles. Now 8 electron in the outer circle. So 18 protons looking out for all these electrons. You have basically 8 protons looking at those 8 electrons in that outermost shell, going to keep them close. So that's due to what we call sort of this shielding effect. There's an attraction to the nucleus for all the electrons. However, as there are more and more inner shell electrons, so things like here, the first 2, the 10 electrons here, these are repelling each other and the ones further out, and that repulsion sort of allows for an expansion of the radius. And we call that a shielding effect. It's the reduced attraction for outer electrons to the nucleus due to the inner electrons sort of pushing them away. And we tried to demonstrate that outside. So that's all I'm going to go over right now, and I hope that was helpful. I think I'll post that. That wasn't awful. Have a good night. Bye.